However, today I will try to share with you some of our novelties in studying postural control and motion sickness. It's a little different line of work compared to what I'm usually doing with image, because here is we're looking into brain electrical activities, heart rate, and muscle activities in order to quantify postural control, because postural control is a very complex system which we deal every day and every time we are reacting or activating movements. And it's a combination of different inputs, and with vision, vestibular systems, proprioception, somasensory systems. They work all together, and when one of those input is not compatible with the others, then we don't feel good. Okay, I'm obviously trying to make it simple into a feedback systems that is not at all simple. Ugo, can you have to switch on the microphone. Turn on the microphone. Ugo, I cannot hear you. You are mute. Hello? Oh, okay, maybe it's...
no, I think that the problem is to widen the slides because it's not...
widen the slide?
Yeah, okay, sorry. Okay, everything else was okay. Okay, so I'll continue. So once one of those systems it's in conflict with the others, then we don't feel good. We have different conditions which we can summarize with motion sickness. Our first approach, because I'm gonna divide my presentations in two parts. One is associated to our work in assessing postural control, and the other into motion sickness. And the tool that we are using to quantify the progress of postural control is the brain electrical activities. Why are we doing that? Because we need to assess what is happening during time with a very high temporal resolution. And the EEG, the brain electrical activity, is the right tools. Imagine that with the modern technology, you can acquire signals with a frequency of 10, 15,000 hertz, meaning 10,000 and more samples every second. So we are really able to see the changes in the brain while the cortical remodeling is taking place. So the initial aims is to design a methods to quantify cortical changes during postural control performance. And more specifically, we wanted to assess two different phases of postural control. The initial response to sudden abrupt balance perturbations, which is defined as adaptation. And the second, as when prolonged postural control take place. So when this stimulus is continued again and again, and then finally we get habituated to that. Okay, so these are the two actions that we want to, the two segments of the postural control that we want to measure. And for this reason, we built a measurement setup. So the measurement setup is based on a force plate where we can monitor the stabilograms. And here we have a very powerful stimulator, is a vibrator, and it makes the calf muscles vibrating. and that creates instability in the posture. And then we monitor the effects of this instability with the EEG. All those sensors, they are synchronized so that we know exactly every time that the stimulation is on, what is the response on the cortical level. And we do this experiment 2 times, and once with the 64 EEG channels, and the second time with 256 channels, which is the highest density of electrodes available on the market. What is the reason of having many electrodes on the head? We know that you can actually measure a decent EEG signals even with 8 electrodes. But having a very dense distribution of electrodes obviously gives the possibility to hear the electrical activities in a lot more defined way. So, but the next question is, how do we define adaptation and habituation? And these are 2 segments of the postural control feedback system. And we wanted to define ourselves these 2 segments by measuring the 30 individuals that underwent this experiment. And while they get vibrated on the calf muscles from the quiet stance phase, their sway increase dramatically, with open eyes and a lot more with closed eyes, as we can imagine. So imagine you suddenly get stimulated on the calf muscles and you start to sway on the platform, and the platform can monitor, can assess the changes of the center of mass while this vibration takes place. So the big shock is obviously in the beginning. Then later, after 30 seconds, we have a first sign of habituation, because then the sway, even though the stimulation continues, then somehow we are able to face those perturbations a lot better than in the beginning. But obviously still keeping a lot of the differences between doing this with open eyes or with closed eyes. Then going forward into the experiment, we still have a decrease, and both in open eyes and closed eyes. This, of course, is an averaged value over the cohort. But then suddenly, towards the end of the experiment, we registered an increase on both cases. And how do we explain that? We explain that because obviously now we know and we expect this vibration, but we are also tired to face this vibrator on the calf. So here overcomes fatigue from our point of view. So for this reason, we define the adaptation, the segment in the beginning, the very beginning, the Q1 minus the stance, so the quiet stance. So this first segment is what we call adaptation. And habituation, then it's what follows. So the process, these intervals of time while the body reacts and know how to react to this perturbation. Well, we have done 2 publications on this study, one from the results from the 64 channels and one from the 256 channels, the same cohort. What is interesting for people that is not familiar with the topological plot of EEG, what are you seeing here is the power density of the EEG signal. So meaning the intensity of what we measure on the cortex while the experiment goes on during the adaptation period and during the habituation periods. Unfortunately, this distributed power for all the cohort, in this 64 channels arrangement, they give an indication. There is a distributed trend of power, but is not significant. However, is an indication that there is a distinct rearrangement on the cortical level between the two phases. So meaning that the brain that normally is doing all kind of things, it has not a random behavior during these two phases, but a distribution of power that is kind common in between individuals. But more significant in this study was the connectivity, the brain connectivity, because we can see the brain as the connections in small areas, and that's measured by an index that is called segregation, or with a connection in between the small areas. So it's here it's the local network of the brain, and here is the general network of the brain. So how different areas of the brain, they are connected to each other. Well, in this study with 64 channels, even though we didn't find any significant results for the power spectra, so the intensity of the signal on the cortex, we do find a significant results for the connectivity. So we have differences between adaptation and habituation, and a significant increase in the theta band that is observed on the central eparietal regions. So meaning that the reorganization of the network is in the local organization of the network, it's always configurating in the same way when you have closed eyes, when you are looking into small networks, when you are looking into the signals on the theta band. But what about the integration? So how about the communication in between areas of the brain? Then here we also registered a significant decrease here in the alpha band from the baseline to the adaptation to the habituation. So also here we can see a standardized configuration of the brain activities, in this case connecting between different hubs, so between different areas of the brain in the alpha band. Moving forward, we did repeat the study with 256 channels, and the main difference from a previous study, and you can also here find results published on journals. These are all done in 2020, 2021. But here now, by increasing the number of channels, we finally find also significant results on the topological. So we can really see the distribution of power on the scalp during habituation and during adaptation. So this is a very, very important. The rest of the results, they of course, they are similar. We can see a big difference between the displacement, the sway when the person is on the platform and there is no stimulation, or when the stimulation is going on. And this changes during the experiment, and is still very different between open eyes and closed eyes. So to conclude this first part of my presentation, what is the learning outcome from these two experiments? There is a correlation between the role of the cortex and the cinematic response in body sway. So we did find quantities that is associated to the action of postural control. So when we are swaying because of a stimulus, actually there is a configuration on the brain that is repeating itself. And our findings is also telling us that the visual feedback is something that we can quantify in the signal. So with or without open eyes, then the waveforms, it's completely different. Of course, it's expected, but here in this experiment, we could demonstrate the quantities behind the visual feedback. And the third is this work, these two projects, these two measurements set, they display the first evidence of local and global brain networks that is changing during the postural control. So meaning from quiet stance to adaptation towards habituation. So now we need to do a little step from postural control to motion sickness. And we know that the two dynamics, they are related to each other. The greater postural control instability is correlated with the changes, the susceptibility of motion sickness. So meaning that if we are swaying and we are moving on a boat or driving in the car and we are not the drivers, we are not the skipper, then for many people there is a trigger of motion sickness, of sea sickness, car sickness, air sickness. And this motion sickness, it's not just because of one reason, it's a multiple cause. And recently we had to the conventional way that we feel sick, also the virtual reality. So not only see car, but also virtual reality environment that can mimic and replicate conditions where people normally are getting sick. And there was a video that I wanted to share with you, but obviously it doesn't like. Okay, so no video where, but I show you directly the setup of the lab that I opened 1.5 years ago, 1 year ago, basically, because then with COVID, we only recently did start to work in full speed. So this lab is an evolution of the setup that I showed you earlier. So here we are defining an environment where people usually might get sick, right? And as you can notice, while this experiment goes on, we are measuring muscle electrical activity, then here there is heart rate sensors, and then here we have brain electrical activity. And then these are sensors for the position, so it's a force plate, so we can associate to the movements also the mapping of the center of mass. And what we do here, as you can see, there is a sea environment, and we can calibrate the intensity of the waves, their amplitude, and this is all synchronized with this moving platform. So this is the schematic representation of this new setup. So the goal is to remain still the same, but with an addition. Here it's not anymore just the movement, so the adaptation and habituation, but here we want to trigger the condition of seasickness. So we want to see how sensitive people are to environments like that. And if they are very sensitive, then we want to see if there is a physiological quantity that is a label from this for this sensitivity. So basically, we want to associate quantities to motion sickness. And I need to tell you this story because I found it very incredible, and I'm very proud of this because during COVID, my class of medical instrumentation, they did the first study that we just published. because there was COVID, we couldn't host people from outside. So we just measured ourselves during the class. And from these measurements, we have this first scientific work from the motion sickness lab. And basically, all the people before starting the experiment, they are tested with the motion sickness questionnaire. It's the gold standard to assess motion sickness. So they do respond a standardized questionnaire before and after the experiment. In the experiment, we have a progressive increase of intensity of the wave, and we can select, let's say, a soft protocol and a hard protocol. I have to tell you that it's not more, you are not getting more sick if there is more turbulences in the sea. It's just a movement, because when the sea is very wild, then you are so concentrated in the stability that you are not thinking about the motion sickness. So actually, we wanted to test this hypothesis as well. So this first study on the student cohort, they displayed the importance of all the parameters that we measure. And I have to give a little order here, because we do extract what is called features. So meaning from all the measurements, we do post-process the signal and extract some values. So we have 5 values extracted from the EEG, and then we have 10 values extracted from the muscles, and 2 values extracted from the heart rate. So those parameters, they are all put together, and in order to see if we can predict the symptoms. So because the symptoms from the questionnaire, there were many, we just grouped them in 3 main index. One that we call the physiological vegetative index, that includes sweating, salivation, nausea, burping, stomach awareness, and general discomfort. And the neurological muscle strain index, which includes fatigue, eye strain, difficulty of focusing, headache, fullness of head, blurred vision, and general discomfort. And then it's basically the total of those 2, so the extraction of those 2 together, that gives the motion sickness index. So the good news is that by putting all these parameters, the parameters that we measure, all the parameters that we measure, we are able to predict those indexes. But most interesting is from where the prediction comes from. The prediction comes from, and this is the importance of each parameters in terms of prediction. Then you see that there are the areas, if you read here, is the areas of the muscle contraction that scores the most. So it's the most important value to take into account while measuring motion sickness. And of course, all the others. I mean, if we would measure only the area of the muscle electrical activity, then we will not predict anything. But this, plus all the rest, it gives the possibility to predict this physiological vegetative index, neurological muscle index, or motion sickness. So meaning we can assess from the way that your physiology responds if you are or not sick. Moving forward, then we could finally also measure other people than my class. And we were lucky because in our university, there was an ongoing study measuring reported uncomfortable feelings, and they associate these uncomfortable feelings to the vibration on the earth. So what a better way to give them a comfort, meaning to give them a quantity and to try to study if this motion sickness is the same of what we know or it's something different. The results on the next Padua Muscle Day, and I thank you for your attention. And of course, I have to acknowledge my team and particularly the students that are doing all the data you see on the slides, and our clinical partners, Hannes, that he is our, let's say, the ideators of studying the postural control with quantities. Thank you very much, and I will be happy to address questions or curiosity.
Thank you so much. I was really fascinating by this presentation because there is really an unusual approach, very interesting. I was wondering about the role of aging in this pathway. So if you are planning to evaluate also old age people to see the role of this situation when you start to have both muscle and visual problems. And I was wondering also if you are thinking on the possibility to use this system first to detect the risk of falling, which is one of the main problems in old age population. And the other one, if it is possible to think about the possibility to use this system, for example, for rehabilitation, because the fear of falling is one of the main problems we have with old age people, especially the ones who fall, who had, for example, a hip fracture. So I see a lot of ideas about these topics in your project.
Thank you very much for the question. That's why I said towards the end of the presentation, this is just the first little scratch on the surface. We have been more concentrated in finding reliable quantitative tools. So that has been my main goal in this almost 2 years of research, because everything that you can read about this work from our group is very recent. It's very recent, and it goes into assessing, is it possible to do it? Then the application, as you mentioned, this is incredible. I mean, the postural control is one of the problems that aging people, they do have. So we could customize the virtual reality test in order to give them more suitable training platforms. And then that goes also, just yesterday I talked with the neurosurgeon, and he was mentioning that he wanted to start to send to us people after stroke, just to learn coordination and also to have a quantitative assessment, because this is the real challenge, because many of those things, they are already performed somewhere, but not yet with quantities. It's not yet possible to give a quantity to a physiological condition of this type.